Today we're going to talk about X-ray production. X-ray radiation is produced in an X-ray emission tubes by colliding electrons with the atoms in a metal. There are two types of X-rays that can be created through this method. The first are characteristic X-rays, and those X-rays are created by knocking electrons out of the shells of the atom. So here we've got the atoms in the target metal. So here, the atom with the electrons orbiting in shells. It's not what it looks like really, but this is a good enough approximation to demonstrate how these X-rays are emitted. So an incoming electron, electrons that are fired at the atoms in the metal. The electron comes in and it knocks out an electron in one of the lower shells, in a shell that's low down, a lower energy level, at a lower quantum state. It comes in and it knocks it out. So here we've got the electron has knocked out, the initial electron here has knocked out the other electron, leaving a blank space in the quantum state that needs to be filled by electrons of a high energy level. And to fill that void, to fill that gap, one of the electrons in a higher energy level drops down to the lower energy level. And to conserve that energy, it gives off energy in the form of an X-ray. So once again, the stages, the electron comes in, knocks out an electron in a lower shell, a higher electron level, an electron with a higher energy level, at a high energy level, in a higher quantum state, drops down to fill the void, and in that process, that energy level change, that change in vibration, that change in that quantum state, emits an X-ray, and it's the actual difference in the energy level is the energy that the X-ray will have in order to satisfy conservation of energy. The second type of X-ray that we can have that can be produced is called Bremsstrahlung. Bremsstrahlung is a German word. It means breaking radiation, breaking as in slowing down. So in this scenario, the electron isn't stopped necessarily. The electron isn't knocked out. It doesn't interfere with any part of the atom in the metal. The way this works is that the negative charge of the electron that is incoming, that is being fired towards the atom in the metal, is slowed down. It moves in a curve around the positive charge that is the nucleus of the atom. So the electron slows down and moves around, okay? And during this point, it's being accelerated. It's being accelerated. It might not change its speed, but its velocity changes because its direction is being changed. And therefore, its velocity is changing. Its velocity is changing because it is being accelerated by this positive charge. It's having its direction changed. Because its velocity is changing, that means its energy might change. Its energy, if it does slow down, if it changes its kinetic energy at all, there needs to be some balancing out of that energy. The energy doesn't just evaporate or go nowhere. The energy, the leftover energy from slowing it down is converted to an X-ray. And as you can see, depending on how close the electron goes, how much it's slowed down by the nucleus, how much it's slowed down will change the energy that the X-ray will have. If it's not slowed down very much, then a very low energy X-ray is emitted, and if it stops the electron completely, if the electron is completely stopped at the absolute other extreme, and then the X-ray will have a very high energy. So you can see there are two very different ways where X-rays can be produced when you are firing electrons at very, very high velocity towards a metal. So how are those electrons affecting? How do they affect the actual energy of the X-rays that are being given off? Well, if we're looking at just the characteristic X-rays, the frequency of the characteristic X-ray is determined by the change in the quantum state, the change in the energy level, and it depends on the target metal often as to the difference between the energy levels and the amount of energy that's given off. It'll be a very defined amount, though, because of the change in quantum state, the change in energy level is a quantified amount. It's a single amount. If we have a look at this diagram shows exactly where these characteristic X-rays, the intensity of them. You can see that there's a spike at these two characteristic X-rays being given off. It's because these points are these two defined energy levels at this amount of energy X-ray being given off, and this particular amount of energy X-ray being given off. If we're looking at Bremsstrahlung, however, it's determined by the change in kinetic energy of the electron. So the energy in needs to equal the energy out. The energy before any sort of interaction with the electron and the metal needs to be the same as the energy after. So if the metal is at rest, with relation to the electron, then the only initial energy that is in the system is the kinetic energy of the electron. So this is the kinetic energy of the electron is equal to the initial, kinetic energy of the electron is equal to the final kinetic energy of the electron plus any leftover energy is emitted as the X-ray. So this is the additional X-ray energy that's left over from the slowing down of our electron. The absolute maximum energy that we can get out is if this value becomes zero. So if the kinetic energy of the electron becomes zero, it is stopped. It has no energy left. All of the energy that it once had is converted to an X-ray. So all of that energy, that initial kinetic energy, becomes the energy of the X-ray. And it's helpful to remember that this means that for the maximum kinetic energy, the maximum kinetic energy transfer, this would be the maximum amount of energy. It'll also be the highest frequency, the maximum frequency, and it'll be the lowest wavelength, because the lowest wavelength corresponds to the largest energy. So in here, all the kinetic energy is converted to X-ray energy. So here on the graph, this is the Bremsstrahlung, and it's a continuum. It's not in the distinct peaks like the characteristic X-rays are. It is spread over a much larger range of wavelengths. Here, this being the minimum wavelength, the absolute smallest wavelength, that'll be the highest energy, the absolute highest energy that we can get from our collision with the electrons, and the metal. So this is going to be the maximum energy. It's the minimum wavelength, the smallest wavelength. And the continuum will slow, will gradually decrease as we go further and further, as less and less energy is transferred to the metal from the electron. So this corresponds to the electron being slowed down less and less. You can see that the intensity of these spikes, the characteristic X-ray spikes, is much, much larger out of the Bremsstrahlung sort of continuum. All that is indicating is that these particular frequencies of X-ray are given off much more often than all of these other Bremsstrahlung frequencies, individual Bremsstrahlung frequencies. That is not to say that the characteristic X-rays will occur more often than Bremsstrahlung. You can see here that the area under the curve, there's a much larger area under the curve for Bremsstrahlung than there is for the characteristic X-rays. There's much more energy is going to be given off as part of Bremsstrahlung radiation, and the reason for that is it's relatively uncommon for the electrons to actually strike another electron. It's more common that they'll be slowed down. The reason that we've got these particular spikes is because they're a quantified amount, whereas here we've got a continuous amount of Bremsstrahlung radiation. So here we've got 3 examples. I'm not going to read them to you, but we can go through the actual answers for them. So for the first one, we've got an energy coming in of 75,000 electron volts. So we can convert the energy for our X-ray is equal to HF, and this is going to be the maximum frequency. The maximum amount of energy will have the maximum frequency. So the maximum frequency will be the kinetic energy that the electron has divided by Planck's constant, and I've used Planck's constant that is in the units of electron volts per second because that's the energy, the value that our energy is in. And finding that, we find that the maximum frequency that an X-ray could have emitted from an electron with this amount of energy is 1.8 times 10 to the 19 hertz. This is at the upper range of the X-ray. Of X-ray production. The exponent there will often be times 10 to the between times 10 to the 16 and times 10 to the 19. So that's to the upper end, the higher energy end of the X-ray band. Here, if we have a look at substituting in HC on lambda for HF. Okay, so F is going to be C on lambda. Once again, I said that there is an inverse relationship between frequency and wavelength. So the maximum frequency will be the minimum wavelength. So here, HC on lambda minimum is going to be equal to the kinetic energy of our electron. So we can rearrange that here, and substituting in the electron volt seconds value for Planck's constant multiplied by the speed of light, 3 times 10 to the 8, divided by the 500 volt potential that we're accelerating our electron to. So therefore, this is the energy, the kinetic energy that the electron's going to have is 500 electron volts, because it's being accelerated, it's an electron, and it's being accelerated across a potential of 500 volts. Plugging that in, we get that there is the wavelength of it is 2.5 times 10 to the negative 9 metres, so that's 2.5 nanometres for wavelength. Now for this last question, it's probably useful to have a look at this energy level diagram. The different energy levels here, n equals 1, 2 and 3, these are the different levels that the electrons can jump between. They can jump from n equals 2 to n equals 1 and they'll give off some energy. They can jump from n equals 3 to n equals 2, they'll give off some energy. They can jump from n equals 3 to n equals 1 and give off some energy. And so if we knocked out an electron in n equals 1, then an electron from n equals 3 would drop down to fill that energy void. So we've got here that the lowest energy level is at negative 20 kiloelectron volts. The highest is negative 0.5 kiloelectron volts. The greatest amount of energy that's going to be emitted, the greatest amount of energy from an electron that's going to be emitted is going to be the biggest jump it can do, the jump between the furthest jump between the energy levels. So the greatest energy is going to be from n equals 3 here to n equals 1. And the difference between those energy levels is 19.5 kiloelectron volts. That's the difference between the energy levels. So we know E equals HF. The frequency of this is going to be E on H. So the energy we're looking at is 19.5 times 10 to the 3. That's kilo electron volts, divided by the value for Planck's constant in electron volts seconds, 4.14 times 10 to the negative 15. And that yields a frequency of 4.7 times 10 to the 18 hertz.